less conservative and more efficient. We have a classical disturbance observer that is very well known in control engineering, which estimates the term D in real time, and this information plus tolerance bounds are supplied here to the yellow box in order to make the control strategy less conservative. That means less slow than we would have if we don't use this additional feedback session. Okay, here you can see real experimental results that we obtained at our test rig. Here you see these are times in 10 to the power of 4 seconds. That means each of these experiments takes several hours that we have. We have in the dashed line an open loop control strategy for the anode gas. This is just predefined. And the cathode gas is used here as the physical system input to make sure that the corresponding temperature that you will see on the following slide follows a desired trajectory with good accuracy. And here the splitting up of the preheated temperature, the solid line on the left-hand side and the corresponding solid line for the mass flow on the right-hand side, they are being calculated here by the optimization procedure that we had seen on the previous slides. Now, here you can see the results. The desired stack output temperature is the dashed line for the heat up phase of the system. And on the right-hand side, you can see control errors, let's say from an interval of -60 to 60 plus 6 Kelvin. And this is very accurate if you assume that you can measure temperatures in the interior of such a stack module, let's say with certainly not more than 10 Kelvin accuracy. This is within the measurement tolerances already. Now, in order to have a look at what can be really controlled and what not, we can perform an offline analysis of the influence of actuator constraints. Then the white line that you can see is the desired trajectory from the previous slides. And we can, there's also a bisectioning strategy, we can determine control error intervals around this white line, which we can distinguish for different sizes of the uncertainty and for different amplitudes of the variable structure part in the controller, which we can distinguish between dark gray regions, which are guaranteed to be stabilizable, and which can be also realized by the control strategy, since they're in the interior of the actuator constraints. These middle gray regions, they overlap with the actuator constraints, with some spinning on the top. And the light gray regions, unfortunately, violate the actuator constraints, and these are certainly not suitable operating ranges for our system. And here you can see we can shift these regions here by just adapting one of these parameters, and this parameter is the parameter eta tilde. This is the parameter that is scaling the variable structure part in the control law, and using a suitable online search scheme for the optimal value, we can define also control strategies here on the top for high temperatures, which prevent overheating here in the interior of the fuel system. Now, there's one problem. The problem still is we have guaranteed contraction towards the desired operating range of the system, but what we didn't do is we didn't calculate this optimality criterion simultaneously with the stabilization of the system dynamics. And for that reason, we could have the idea to use a predictive control strategy, which is predicting the system output temperature here, the temperature Y, over a number of NP time steps, and comparing this predicted temperature with the corresponding desired outputs. And what we want to do then is we want to minimize the deviation here. For example, this is a quadratic cost function here. We want to minimize J by a suitable choice of the system input. Yes, and for that purpose, we can calculate the differential sensitivity of this error measure. This can be done in a suitable form by algorithmic differentiation. That means you don't have to do this analytically. And we can define, using this information, a resource constant control strategy, which makes use of an interval pseudo-inverse afterwards of the corresponding partial derivative of this error term with respect to the steps in the control signal. And as I mentioned, we can compute all required partial derivatives here by means of algorithmic differentiation, which certainly increases the efficiency from a computational point of view. And we can account for worst-case error bounds here in the interval evaluation of J, and these error bounds result from parameter uncertainties and from measurement tolerances. Now, we have a quite similar cost function that is being used. It's more or less the same than we had on the previous slide, just a few redefinitions of parameters here. And what we additionally parameterize is a desired or deviation from desired average cell temperatures here on the bottom, and we penalize overshooting over maximum admissible temperatures. And this is, for example, the choice of 880 Kelvin for our fuel cell state. Now, this is what you see at the end of my presentation. It's a combination of simulations and experiments. What we see here on the left-hand side, the measured anode gas temperature that is being controlled here in our system. It's real measured data. Here in the interior, you even see there's lack of measured data. That means we need in the real-time experiment here something to detect a loss of data in between and to predict what is happening here in between. And we have the measured mass flow of the nitrogen during the heat-up phase. We're switching on, after some point of time, the mass flow of hydrogen to the system. That means we start the electrochemical reaction, which produces further heat. And what we want to make sure now is by the suitable choice of the preheater temperature at the cathode, that the maximum value of the cell output temperature does not violate some given upper bound. This upper bound was this 880 Kelvin, and we only have very small overshoot here in the test rig over this bound, which can be tolerated. What cannot be tolerated is large overshoots here. If you don't use this control strategy, you get overshoots of more than 100 Kelvin, and this leads to the danger of destroying the fuel cell stack module. And just to give you a number, the stack module has an electric power of 1.5 kilowatts, and it costs about 60,000 euros. That means this is certainly something that is worth investigating here, preventing this overshoot. Now, let's conclude the presentation. What you have seen is the basis for all the control strategies is a suitable modeling of a quite complex electrochemical application, where the basis was a parameter identification, and the control design has been performed by two alternative approaches. One is the stabilization of the aerodynamics using a sliding mode control strategy, and the other one is an online optimization of performance criteria within this sensitivity-based interval arithmetic control strategy. Now, currently we're working on some extensions. These extensions are to extend the control strategy also by estimation of non-measured internal stack temperatures. There will also have a sensitivity-based scheme for that purpose, and is to extend also the system model by description of the preheater dynamics, since it turns out that you can't determine instantaneously the preheater temperature without also getting into danger of overheating of the preheater itself. And yes, last but not least, we will extend the scenarios also with switching between the output segments, that we can control the temperature at different segments. And yes, the thing that we have here for this sliding mode control strategy can also be applied for those of you who know backstepping control strategies. They make use of Lyapunov functions internally. The same idea can also be applied for that purpose. Okay, thank you for your attention.
Any questions?
Yes, I have a small question. You said that you have a real-time implementation of the interval controller.
Yes.
But you have some bisection in.
Yes. The number of splittings is limited.
Yes. Ah, okay. Okay. So you know in advance the computing time
Yes.
you will have at each.
Yes, the thing is, when we're let's look here. Here you can see it. We have range constraints for the preheater temperature, and we have range constraints for the mass flow of the cathode gas. These are intervals that we know in advance. From these intervals, we only pick out intervals which fulfill the sign constraint that is described here on this slide using the Lyapunov function. That means arbitrary points within these intervals guarantee asymptotic stability. The only question is which point to choose from this interval in order to get energy efficient operating strategies. And control strategies which also don't violate variation rates, visible variation rates between two subsequent sampling times. That means here you don't get in danger of, let's say, losing asymptotic stability. You can, in fact, choose arbitrary points, you only lose efficiency by limiting the number of subdivisions.
Thank you, Andreas, for that. So my understanding is that in fact you use interval analysis to satisfy the constraints, and then maybe you use a point solver for the optimization, something like that. Within the result.
It's a point solver that is implemented here for the predictive controller. Here we searched directly for a point value. The optimization procedure that is used in this bisectioning scheme that I have in this sliding mode control strategy, this is really searching on interval boxes, and it's taking out the interval box that is the smallest supremum.
Okay.
And there we use directly in the optimization also the intervals.
Okay, back, yeah, as you said, you know exactly what is the computation.
Yes, I know in advance what the computation time is that I can spend, and afterwards I just stop.
So, and then also, you mentioned the interval to inverse.
Yes.
Can you comment on this? How do you do the...
It's just, I have to switch to the previous presentation.
Oh, sorry.
No, it's very easy.
Something.
What Louise had in her talk. She's slightly prepared. Where do we go with? Here it is. It's just evaluating this definition, and this definition works as long as we don't have any problems here with the rank of the matrices that I want to invert. And the rank here is, we have here matrices that have less rows than columns, and this always have full row rank, these matrices. And that means this inverse here on the left-hand side, in my case, can always be computed. And this means it's no problem here, as long as we have really large overestimation in the computation. And this also only leads to loss of efficiency in the case.
Now you said something about computing, but I don't even know what an interval inverse is. I don't know how it's defined.
You try to invert a matrix here according to this scheme.
Pseudo-inverse is for not square matrices, but for rectangular matrices.
It's just
And
extending.
what is the definition of the interval pseudo-inverse of such a matrix? I don't know what it is.
It's a matrix which you multiply here on the left-hand side to this term here, to the matrix
You
GM,
define it by
which includes the identity matrix. I need some approximation here for this minimum non-solution.
Sorry for interrupting.
No, thank you for the phone.
No, it's a good point.
Yeah.
Because you have intervals at which point from this interval is the real pseudo inverse. You're absolutely right. It's a matter of definition.
But one may expect large over approximation when you have a large matrix you have a large matrix, a large dimension matrix, and you want to compute pseudo inverse, you may lose dependency, so maybe it will be, I don't know.
What you can do is, since we know in most cases symbolic expressions for these matrices, you can try to calculate this inverse here by symbolic formula and then plug in intervals. And this reduces those dependency effects.
Okay. And then, that's interesting because I thought about this kind of stuff. And then when you have an output, like when you have a pseudo-inverse, it's an interval matrix, how do you use it for dispatching the image? Because you might expect only point values.
Is at the end?
Yeah.
I have to come back to point values. What we want to do is, we want to make this j, which then afterwards is an interval, we want to make this as small as possible. That means what we are implementing more or less is something like a gradient search. We're searching for the steepest direction where we can reduce j, the supremum of j. And this is being done by this pseudo-inverse scheme. We just plug in on the following slide here this interval pseudo-inverse here in the round bracket. We have an interval for j, and then the heuristic search here for this gradient method is take the supremum of the complete term here on the right hand side.
Okay, so it's worst case.
It's something like worst case gradient search.
And the other-
not a unique one. In case we do
No, it's not unique. You get an interval also for the inverse.